Thank you, Pat, and thanks to the organizer for this opportunity. I'm very happy to come here after so long time and to see many friends and colleagues after so long time. So, in this talk I'm going to discuss a point which was left unanswered by Massimo in his previous discussion, which is the study of the asymptotic nature of neutrinos, or mixed neutrinos, of course. And as you can see from the title, the framework is the weak decay of a proton in the standard model, in the standard theory. Okay. So maybe you may think, okay, you are simply a liar. Well, we know that protons are stable particles, so is it possible to talk about proton decay in the standard model? Well, you're right. We know that protons are stable, but inertial protons are stable. What happens if we accelerate the proton? What happens if we give to the proton enough energy to decay? Well, in that case, I showed you in a while that the process in principle is not forbidden anymore, so the proton can decay, and I show you in a while how is it possible to use this process to test theoretically the asymptotic nature of neutrinos. Okay, so these are the main references on which my talk is based, and they are in collaboration with Massimo Dasone, Gaetano Luciano, and Luciano. And these are other works which go more or less in the same direction, and some of these works are from authors in the audience here. Okay, so that's a brief summary of contents. I will be very, very fast on this introductory part because it was explained by Massimo a few minutes ago. So let me just remind you the main difference between mixing in quantum mechanics and mixing in quantum field theory. So in quantum mechanics, we know, thanks to Pontecorvo, we know that flavor and mass basis, they are connected by a simple, here I'm considering a two-flavor description, simplified two-flavor description, but we can extend the same consideration to three flavors as well. So we know that these two bases are connected by a rotational unitary, so there is basically no difference between these two bases in quantum mechanics. Okay, you can work either in the mass or in the flavor basis without any substantial difference. Okay, that's not true anymore in quantum field theory, because if we implement mixing transformation at level of field operator, one can see, as explained by Massimo, one can see that, for instance, if we focus on the flavor vacuum annulator, which is the vacuum annulator for flavor fields, one can see that this operator is related to the corresponding ladder operator in the mass basis by means of two transformations. The standard Pontecorvo rotation and this Bogoliubov transformation, which is responsible for the inequivalence between the vacuum for flavor fields and the vacuum for mass fields, and so that's responsible for the inequivalence between the Fock bases built on the mass vacuum and flavor vacuum. So, as said by Massimo, this poses a problem, an ontological question, which is the physical Fock space for mixed neutrinos, the flavor or mass Fock space. Okay, in the language of the S-matrix formalism, this amounts to asking, for instance, which is the base to be used for the computation of the S-matrix elements, the mass or flavor basis. Okay, so that's basically the question I'm trying to answer in this paper. Okay, you may wonder if this is just a mathematical curiosity, just a theoretical curiosity. The answer is no, because, well, if we try to consider the intensity of the tritium beta decay versus the kinetic energy of the emitted electron, you can see, well, we can neglect the blue curve, which is for asymptotic massless neutrinos, but we know that neutrinos are massive, so let's focus on the orange and green curves. You can see that here there is a very, very small but non-vanishing difference between these two plots. So, in principle, we expect that such a controversy, flavor mass, may have some experimental implication as well. For the moment, we cannot access such a scale, energy scale, so we don't have any kind of experimental feedback, but in the future we expect that this might be possible. So that's not just a theoretical problem. Okay, the other tool which is important for my talk is the Unruh effect. Very, very briefly, what is the Unruh effect? This is a prediction of quantum field theory which states that from the point of view of a uniformly accelerated observer, the inertial vacuum is not completely empty, but it appears that a thermal distribution with a a temperature proportional to the acceleration of the observer. And this was shown in this seminal paper in 1976. Okay, now let's go to the study of the proton decay. That's a brief review. As I was saying, inertial protons are stable because of the conservation of baryonic number and energy conservation. But what happens if we accelerate the proton? Well, as I was, if we kick the proton, we accelerate, we give energy to the proton. In principle, this process is not forbidden anymore. So the proton can decay into a neutron, a positron, and an electron neutrino. And we name this process inverse beta decay. Here we have just a semi-classical estimation of proton lifetime for characteristic values of the acceleration. Okay. Well, this is what happens in the laboratory frame where the proton is accelerated. But now the question is, important question is, what happens, for instance, in the comoving frame? And when I say comoving, I mean the frame co-accelerating with the proton. In this frame, of course, the particle is at rest, so the decay should not occur. But that's not the case. The process, the decay, occurs also in the comoving frame, thanks to the Andrew effect. Indeed, what happens? It happens that the proton, in some sense, has memory of its acceleration also in the comoving frame, and so you can see that the proton picks up an electron, or maybe an antineutrino, or both, from the thermal distribution, and this interaction is responsible for the decay also in the comoving frame. So at tree level, this is at tree level, we have these three processes in the comoving frame, which are the counterpart of the process in the laboratory, of this process in the laboratory frame. Okay, so the process can occur also in the comoving frame. Okay, the first computational approach to this study was made by Massas and collaborator in his work of 1999. This is based on a series of reasonable approximation. They consider neutrinos as massless, so no mixing. And well, they use the semi-classical Fermi theory to describe the interaction, which is good as far as the acceleration is much smaller than the mass of the boson medium. I want to skip technical details, just let me jump to the result of this paper. If we compute the scalar decay rate, which is the probability over the neutron over time, this capital T, this is a scalar quantity. Okay, so this is invariant by definition in a generally covariant formula like quantum field theory. So we compute this scalar decay rate. This is the result in the laboratory frame. This k is a Bessel function. We make the same computation also in the comoving frame, and one gets perfect equality between the two decay rates. And this was exhibited initially as a theoretical proof of the necessity of the Unruh effect for the general covariance of quantum field theory. Because without the Unruh effect, the two decay rates would be different. Okay, so this would imply a violation of general covariance of quantum field theory. Okay, here just a plot of proton lifetime versus the acceleration, and as you can see, the lifetime decreases for increasing acceleration and vice versa. Okay, now what happens if we try to include mixing in this framework? Okay, the first attempt was made by Alvalia and collaborator. The author says that while in the laboratory frame the interaction is the standard electroweak interaction, so neutrinos, asymptotic neutrinos are in flavor-eigen states. On the other hand, in the co-accelerating frame, they say, they just claim, there is no strong mathematical arguments, they just claim this. They say that in the moving frame, the proton interacts with neutrinos in Windler states. Windler means uniformly accelerated. And they say that in these states, neutrinos display an effective thermal weight, so they are massive eigenstates. They also observe that if flavor eigenstates were used also in the comoving frame, then the thermality of the Unruh effect would be violated. They consider the thermality of the Unruh effect as holy in some sense, so they don't want to violate the thermality of the Unruh effect. So they work in this framework, and they conclude that the two decay rates disagree when including mixing in this framework. But as I was saying before, of course we cannot accept, we cannot share such a result because it implies a violation of the general covariance of QFT. So, well, we don't accept, we don't share this result. In some sense, we consider the general covariance of quantum field theory as a sort of lighthouse. We want to preserve, we start from this requirement. We want to preserve the general covariance of quantum field theory, which is fundamental for any theory, the ingredient fundamental for any physical theory. And we want to see what happens to the other ingredients of the theory. Okay, so we start from the general covariance and then we see what happens to the other ingredients. So, in some sense, we are the paladins of general covariance of QFT. This is me, Massimo Blasone, Gaetano Luciano, and Luciano Cavicillo. Okay, well, first we notice that it's not true. As far as we work in the Pontecorvo approximation, it's not true that the thermality of the Ugo effect is violated, and the computation is very easy to follow. Indeed, if we start from these states, from these flavored neutrinos, which is a superposition of U1 and U2, one can see that if we compute the vacuum distribution for this guy here, we can see that this is simply the sum of two Ambrose distribution, but this omega, notice this small omega, which is the Rindler frequency, it does not depend on the mass of the object. So this, for μ1, is the same as this for μ2. So here we can factorize this distribution, this is unity, and so we get the same result as for massive neutrinos. So there is no violation of thermality of the Ugo effect if we work with Pontecorvo states. And now we are working with Pontecorvo states. And also while I was working with Pontecorvo states. So no violation of thermality, okay? So Humluch is happy, no violation of thermality. Well, honestly, a slight deviation from thermality can be found if we work in a full theoretical field theory. But so if we use exact flavor states, but that's another story. I'm not using these states, I'm not working in this framework. But in that case, one can see that distribution is indeed non-thermal, because you can see this is the standard Unruh distribution, and these are corrections which arise from mixing. Mathematically, this is due to the fact that the Bogoliubov transformation responsible for mixing has a non-trivial interplay with the Bogoliubov transformation responsible for the Unruh effect. So this combination gives a non-thermal distribution. In that case, Unruh will be surprised, maybe even upset. But again, that's not the framework I'm working in. So Unruh effect is perfectly thermal, no violation of thermality. Okay, so this claim is basically wrong, no violation of thermalities. So there is no need to insist on the usage of massive states in the cooling frame. And indeed, our position, our claim is that the correct representation for asymptotic neutrinos is the flavor representation. Let's see what happens if we use asymptotic flavor states both in laboratory and cooling frame. I skip again computation. I just jump to the result. So this is the decay rate, the scalar decay rate in laboratory. This is the scalar decay rate in the cooling frame. As you can see, the structure is the same. Two diagonal terms and an off-diagonal contribution, the same here. It's quite easy to show that this guy is equal to this guy, the same for these two. So the focus is on these last two terms. If they are equal, flavor states are consistent with the general covariance. If not, well, there is a problem also with flavor states. Let's see what happens. Okay, well, analytic computation are non-trivial, but if we work in this approximation, which is quite reasonable for ultra-relativistic neutrinos, to the leading order, one can see that these two off-diagonal terms are equal, so the two decay rates are equal in this approximation. Okay, so it seems that flavor states work well, at least in this approximation. Okay. So it seems that flavor states are the correct representation. It seemed to be the end of the story, at least initially. But quite surprisingly, one day later, just one day later, we submitted our paper on the archive. Another work, still by Matsas and collaborator, appeared on the archive, and they claim exactly the opposite result. That is, mass eigenstates are consistent, are the correct states because they are consistent with the general covariance. But let me try to convince you why this framework, even if it's consistent with the general covariance of quantum field theory, it cannot be regarded as the physical framework. Okay, well, basically, Matsas and co-worker, they say that a physical Fock space for flavored neutrinos cannot be constructed because, so these states can be defined only phenomenologically, so the fundamental states are the mass eigenstates. Well, first, it's not true that we cannot construct a physical Fock space for flavored neutrinos, and this was shown in this paper by Blasone and Vitiello. Then, if we work with massive states, this implies a violation of lepton charge in the vertex, which is at tree level, which is at odds with the prediction of the standard model. Then one can see that if we use massive eigenstates, there is no sign here of the off-diagonal term. So this off-diagonal term is indeed arises from the interference between 1 and 2. So this is the term which is responsible for flavor oscillation. If here there is no sign of interference, it's not clear how to describe oscillation working with massive states, but we observe oscillation. So, and finally, maybe the strongest point, the use of massive states is inconsistent with the prediction of a CP violation in neutrino oscillation. So these are the arguments we use to reject, in some sense, the result. On the other hand, let me show that flavor states are consistent with all these requirements. Okay, so this is the process in the laboratory if we neglect oscillation, and we commented above. This is the process if we take into account oscillation. So as you can see here, I'm considering an electron neutrino, which asymptotically oscillates into a muon neutrino, and the other guys are the same. So this is the decay rate for this process. As you can see, this is a pure interference term, because it is related to oscillation, as I was saying. We sum over these two terms, and we get this very simple expression. Okay, thank you. The same in the moving frame. So here, I'm just saying, we are just saying that neutrino oscillation occur also in the Andrew distribution, because, for instance, if we look at this process, here we are saying that a proton picks up an electron anti-neutrino, which was originally a muon anti-neutrino, the same here. So we are saying that neutrino oscillation occurs also in the Andrew distribution. Okay, so we compute the scalar decay rate for these two processes, we sum again, and we get this expression, which is exactly the same as the one in the laboratory frame, because I told you before that this gamma tilde 1 is equal to gamma 1, and the same for 2. So this is exactly the same as the expression in the laboratory frame. So if we use flavor states, these also allow for a natural description of neutrino oscillation. Finally, CP violation. We know that to describe CP violation, we need at least 3 generations of neutrinos, who are not enough, because in that case, we can always set this CP violating phase equal to 0. So we need at least 3 generations. And this is the mixing matrix for 3 generations. Okay, in one of the possible parameterization, this is the standard parameterization. But we know there are also other parameterizations, several other parameterizations. But the most important point is that the only invariant measure of CP violation we can build out of this matrix is this Yarskov invariant J, defined by this equation. When I say invariant, I mean independent of the parameterization. Well, parameterization is just a kind of gauge, so we know that physics cannot be dependent on the parameterization of the matrix, so of course we expect that observables related quantifying CP violation, they must be dependent only on this J, okay? Let's see what happens with flavor and mass states. Okay, massive states, we quantify CP violation computing this difference between the decay rate for the standard process and the corresponding decay rate for the CP violating process. And as you can see here, we just get that this difference is 0, okay? So massive states are inconsistent with the prediction of a CP violation. This difference should be non-vanishing, but with massive states, it's 0. What happens with flavor states? We make the same computation using these time flavor states, and we get first that this quantity is non-vanishing. Second, this quantity is proportional to J, as expected. So flavor states are consistent also with the description of CP evaluation. Okay? And what? That's so good. So just the last slide. This is an overview over the three approaches I presented here. The only one which is consistent with all these requirements, okay, is the one based on flavor states, which does appear as the physical representation. But of course, that's not the end of the story, because there are open problems, open perspective as well. First, we want to go beyond all the approximation we used. Of course, a strong result needs exact calculation or well, very few approximation. Then we want to extend this consideration to curved background, where we expect that the rule of the UNO effect can be played by the Hawking black hole radiation. And finally, to find any kind of experimental feedback, we want to study application of this formalism also to condensed matter system, in particular to superconductors, exploiting the formal analogy between Dirac equation and W of the Gen equation for superconductors, and also other perspective which may arise from discussion with it. Okay, thank you. Thank you.
So, questions?
With the proton decay thing that you just discussed, you said that you have a proton in the lab, and then like you give it a lot of energy, so that it starts accelerating, and then you are considering what happens to its stability. I would like to ask a different question, in which the proton is in the lab, and you're standing. The lab. The proton is standing still, but the observer is accelerating.
Well, that's a good question. First point, I want to specify one thing. At least I want to stress again one point. This is just a semi-classical calculation, okay? In the sense that we are considering the lepton fields as quantum, while the accelerated nucleon current is classical, okay? Because we don't know how to quantize the motion of the uniformly accelerated motion of the nucleon, okay? But I expect another important point. This occurs if you are considering a uniformly accelerated proton, okay? So in that case, to have perfect equivalence, you should consider a uniformly accelerated observer, okay? Which theoretically, yes, is nice, but in practice, I mean, it's not so easy to realize this situation. But I expect that if you consider the situation you mean, uniformly accelerated acceleration, you get exactly the same result, okay? By the general covariance of Clifton.
I don't know, because I don't think so, because like if I'm accelerating and what the neutrino does, what the proton does over there, if I'm accelerating and you're just standing still, I'm going to see something else and you're going to see something else.
So you are saying in that case that you are in some sense violating the covariance, because you are saying that I see something in one frame and something different in another frame.
Yeah, so I should, the observer is accelerating.
But wait, another point, maybe this is...
I think that this is another situation, it's nothing to do with... Actually, this work was, maybe you didn't, it's the original paper is by Mueller, is a physical review, where he refers not only to proton, but also generally to other particles which are stable or not stable, and he was arguing that the decay property of a particle is not an absolute property. This was the idea, but this is quite clear. I think the situation is different. I agree that it should not decay.
Yeah.
At least intuitively. Okay, maybe we can discuss.
Well, okay, but yes, in that case you have to see what happens to the general covariance, okay? Because you are saying that the scalar quantity takes one value in one frame and another value in a different frame. So, okay, thank you. In any case, make a difference.
Yeah.
Yes, well, it's a naive question for quantum optics. So in quantum optics, we also have rotations, like propagation of photons in birefringent media. We also have Bogoliubov with squeezing, etc. So is it possible to match or to make an analogy? If you have a propagation of photons in a birefringent nonlinear medium, would you have similar effects?
I would be happy actually if this is possible, because as I said in the end, we are trying to look for experimental situation which can give us any kind of feedback. So I hope so. I hope so.
If I can add here, however, this is a relativistic field, so there are particles and antiparticles. So actually you have 4 modes which are involved. But the analogy has been used
yes,
by intelligence to a model of
yes, mathematically the Bogoliubov is not, I think it's not the same as was saying Massimo, but physically maybe the result could be the same, or some analogy, we can find some analogies.
In this particular picture, you are taking neutrinos Dirac, huh?
Sorry?
You take neutrinos Dirac. Can you do similar calculations or analysis for the Majorana case?
Yes, good point. I mean, to be honest, this was one of the one of the suggestions by the referee in one of our papers. We were the referee. No, but we expect that the same computation can be also for Majorana, because an important point is that the Euro effect still holds also for Majorana. So all the ingredients we have here for Dirac holds also for Majorana. So we expect that the same result holds also for Majorana. Thank you.
Okay, so let us thank the speaker again.